It's shared.
Cos theta.
Write the sum of
Hello, good morning. I hope you can hear me well. I left this number for you to try. You don't have to finish it now, but it is also in the book. You can continue working on it, especially part 2. But just to make sure that everybody is on the same page, I'm going to try and work with you through the truth table. So this question is saying that we have 4 inputs. We can say D, C, B, A. We can also say A, B, C, D. It doesn't matter. And we are saying that we are saying that the output, which we can call X, is high only when input A is low at the same time that exactly two other inputs are low. So it means B or C, or A is equal to 0 and B is 0 and D is 0, or C is 0 or D is 0. So in other words, you have a scenario where you have in your truth table, let's say A, B, C, D. For these four, at least 3 of them should be 0, and the other one must be 1. When this situation happens, you get a high. All the rest are low. Okay, so that is really what the expression is saying, and then you go through the process. So for the ones, for the combinations which give you a high, you create their product forms, and then you do the sum of products, and then you try and simplify. So today we want to look at a method of simplification called the Kanoff map. Kanoff is a guy, so Kanoff map. We also just like to call it a K-map. Okay, so if I say K-map, I mean a Kanoff map. And I think I said last time that this is a graphical method that simplifies logic equations. In fact, if you do this correctly, it will take it to its simplest form. If you get an equation out of the K-map and you realize that you can simplify it further, then it means that you are mapping, in other words, your analysis of the map, as we are going to learn today, was not done correctly. So you can do two things with this method. You might start with a truth table. So for instance, in this question, you get your truth table, right? But also if you have an equation, if I give you an equation and I want you to simplify it, you can also insert that equation into the truth table. We can work with this for any number of inputs, but the larger number of inputs basically make the situation more complex. And so in this book, we stop at 4 inputs to manage complexity, but we need to realize that this stuff can also be done by computer programs. And so when you usually have computer programs running them, you can work up to any number of inputs. So we can see we have our X. Remember, these systems can have a number of outputs as well, but each output has its own distinct Boolean equation. Now the steps perform this kind of mapping method. At this point, the steps may not make sense because we need to go straight into the we need to go straight into some examples so that we can see how it works, but I just put the steps here. Usually you start with a complete truth table or equation. Okay, so this is a large equation that you would like to simplify. Then you draw a graphical map, okay, showing all the inputs and corresponding outputs. So in fact, okay, so you draw a graphical map, you draw a graph, it's like a graph with, boxes. And for each of these boxes, you have a corresponding output for different combinations. So if you are A, B, C, D, 0, 0, 0, 0, maybe on the output, you get a 1, then you put a 1 somewhere in this box. If it is a 0, you put a 0 somewhere, and so on and so forth. On point 3, we do what we call looping. So we create a loop, and these loops are the ones actually that allow us to simplify the equations. So the loop, let's say we have Actually, we should have something like that. Let's say we have a 1 0 1 0 0 0 1 0, something like that. We find certain, just to be clear, that we loop ones, we never loop zeros. Zeros never get into our loops. So we can find these two and loop them together. And when we loop them together, we get a simple expression for them. This one here, we can loop it as well with whatever we are going to be going through the approach. You know, how do we loop, which one do we loop with which one, and why, and so on. We are going to look at that. And then for each of these loop, you create an expression. And that expression, once you have 3 loops, you are going to end up with 3 expressions. And then you do a sum of product form for those 3 expressions. And that form should be the simplest form. If usually, if you don't loop correctly, you're not going to reach the simplest form if you do not loop correctly. So I want to use the chance to just illustrate some K-maps. Now, the most important, perhaps, let's say we have our K-map like that. Let's look at a K-map. So if you have a K-map of 4 variables, you're going to end up having 16 possible combinations. I think you know that 2 to the power 4 is equal to 16. Or if you have BCBA, these are 16 unique combinations. So we are going to have, these are 16 boxes. Now, on one side, we can put AB, and on the other side, we can put CD. Now, this does not change. So I'm just going to go right ahead and write them the way we do. We usually write A inverse, B inverse, because A can be 0 or 1, B can be, or these can be 0, 1. Then we have A inverse, B, A, B, and then down here we have AB inverse. Now here, similar to this, we are going to have C inverse, D inverse. We are going to have C inverse D. Here we have CD, and lastly, CD inverse. So you can see that the way that these change is similar. We start with A inverse, B inverse on that side. On the upper side, we start with C inverse, D inverse, and so on and so forth. The most important thing here to note is that for adjacent states, okay, because in here I will call these states, you know, this is a state. For adjacent states, so I'm looking at an example like this one and that one, only one variable changes, okay? So every time you move from one state to the next one, only one variable changes. What do I mean here? If I'm moving from this box to this box, A inverse, B inverse stays the same because I'm still, you know, all these boxes mean A inverse, B inverse. But on the upper side, you can see that if I move from this point to that point, you have C inverse, D inverse. Here you have C inverse, D. You can see that there is only one change in state, which is D, which has changed from D inverse to D. Now, adjacent means like neighbor. If I check a state like this one and that one, in this direction, both of them are clearly AB. You know, both of them are clear because AB means all of these 4 states. But if I've moved on the vertical side, if I've moved from this point to this point, you can see that you have D and D, but C inverse has now changed to C. So really, it means that this box corresponds to AB, and then on the upper side, C inverse D, whereas that box corresponds to AB, CD, okay, on the upper side. So as we move, like for example, I'll be with I've seen a chart, I'll be with you in a moment. For example, when you're moving in this direction, you can see that we start with A inverse, B inverse, then we go to A inverse B, only one change in state, B. Then we move next, A inverse B to AB, only one change in state, which is A. And then we move to the last one, which is A, B inverse, again, only B has changed. the same as in that direction. So even as we label these, we try to make sure that only one state changes as we move from one state to the next state. And yes, Edwin, the order matters. And in fact, for the purposes of this class, this is supposed to be the order. Let us stick to this order, all right? I've a habit of putting people out who make noise for us. Arnold. And Lauben, I am going to remove you from the lecture if you cannot mute yourselves. Yeah, so Edwin, please, this is actually the way that we order. It matters, and I've just been explaining that we are trying to change only one position in the states. So if your state is DCBA, only one state out of this should change. You cannot change two steps for you cannot change two states for adjacent steps. Now let me also draw another one here that I again want to use to explain another. So I've started with the big map, which is this is the biggest map that we are going to be working with. But actually the concepts hold for the smaller maps that we're about to see in a moment. So once again, I want to say AB, inverse, inverse, AB, that's inverse, then AB, and then AB inverse. Here it is C inverse, D inverse, C inverse D, CD, and CD inverse. This is how you're going to always do it. Okay, so order matters. And in fact, this is the only order for the 4-state, for the 16-state map. Now, we need to look at this as like a sphere. We need to look at this as a sphere so that these corners, that corner, that corner, that corner, and that corner are corner states adjacent to each other. These corner states are basically adjacent to each other. So in other words, it's as if you have that plane or like a piece of cloth or a piece of cardboard, and you can wrap it around so that these corners touch each other. The problem is that when we are writing here, we look at this in 2-dimensional, but you should remember that this point and that point and this point and that point are actually adjacent to each other. Let us see what we mean. If you look at this point and that point, this point here on this side is A inverse, B inverse, whereas at this point, in fact, we can even look at this state. This state here is A inverse, B inverse, C inverse, D inverse. Okay, so you can see this corresponds to that column and that row. This state here is actually A, B inverse, C inverse, D inverse. So as you can see, it is actually adjacent to this one because it holds. The same will go for this one, which is A inverse, no, A, B inverse, C, D inverse, and then here it will be A inverse, B inverse, C, D inverse. And I think here only state A has changed. The rest is B inverse, C, D inverse, so on and so forth. We are again going to, this one has actually a consequence because, let me talk about the consequence before we go into the maps. The reason why it has a consequence is because we are going to realize that we are looping ones. I already said that we never put zeros in the loop. Okay, so your loop always has only ones. In fact, that is not entirely true. We also have don't care states that we can loop or not. That will come later. The point is that if I have a 1 here and a 1 here, and I want to loop adjacent ones, okay, then this number, and let's say we have a 0 and a 0, then this state or this box and that box are adjacent to each other. So we need to remember that I should create a loop that includes those two together. If you're looking at this and that, these to each other, because we've said that we can wrap around this map. Okay, so let's get into it. First of all, we have a scenario. Don't worry about it. But this truth table is a two-state truth table, meaning that here it's very easy, really. And A, here B inverse and B. This actually does not violate any of the rules that we have talked about, because you can see that this B inverse, this is A inverse B. Down here is AB inverse, and then AB, okay? So if I can redraw the same truth table here, and I have A inverse, B inverse, and B, and then I have my truth table, I can come and find, okay, A inverse, B inverse is a 1, so I put a 1 here. A is a 0, B is a 1, so that's A inverse B, which is here, that's a 0. The A, B inverse, that's also a 0. And then finally, AB is a 1. And now I have filled up my table. Okay, we are going to look at looping in a moment, but for now, let us first concentrate on how we can fill the table. Now, if I had been given the equation, because here you have a truth table, so it's a bit easy, but what if you had been given the equation A, and so you came and somebody said your X is A inverse, B inverse, or AB. We already know that these terms are the points where your output is 1. The terms that are missing, the output is 0. That's why we never resolve them. So you remember, you have your K-map, you get these products. So if I have A inverse, B inverse, I know that is the box for A inverse, B inverse. I know that is the box for A and B. And then I know that the rest is simply 0. This is a two-term circuit, a two-input circuit, and the truth table always looks like this. Obviously, somebody who was asking might say, what if I do, I mean, let us just do it like this, but if you had B inverse and B, A inverse and A, it would still work. But at least we should remember that on the top left corner, where we begin naming our steps, we should start with all inverse. Okay, all inverse. So if this is the case, then you're going to have 1 still and 1. And really, at the end of the day, you'll come up with the same map. Right. Let us look at a three-input circuit. A three-input circuit is drawn like this, okay? So you have your 2 inputs here on one side and the third input on that side. Because there are 3 inputs, this will only change from C inverse to C, but these ones you can see follow the same nomenclature that we have already talked about, which is A inverse, B inverse, A inverse B, AB, and AB inverse. Now, when you are naming, when you are putting your inputs into the map, the outputs into the map, you can see that A inverse, B inverse, and C inverse is a 1. Okay, AB inverse, B inverse, and C inverse is a 1. So you put a 1 there. Then A inverse, B inverse, and C, all right, which is A inverse, B inverse, and C is also a 1. Then A inverse B, which is here, and then C inverse is a 1, right? Then A inverse B, which is again here, and C, which is a 1. Now you have a 0. In fact, you can first fill in all the 1s and the rest will simply be 0s. AB is here, and then C inverse is here, that's a 1, and then we know that the rest are 0s. Okay, so Once you have filled in all the ones, then the rest can be zeros. Obviously, we know that from our map, we would usually now sum up this to create an equation like this, and then we start to simplify. When we are working with maps, we are going to simplify this one using we are not going to do Boolean algebra. We'll just move on from this and we simplify, we do our loopings as we are about to see. Right. You could have drawn this. Okay, so you could say maybe, it depends, you could put A and you could have this could work. I'm sure this could work. Really, I don't see why it can't work. All right, so you have something like whatever you want to put here, maybe A inverse, B inverse, C inverse, B inverse C, BC, and BC inverse. Excuse me. All these should be able to work. I don't see why they wouldn't work, but let us try and maintain this kind of format where you have your AB on one side and C on the other side, or CD or on the other side. And then finally, we have our 4-input map. Again, you have a truth table, but even if you are given an equation like this one, you can actually fill this map. But let's look at the truth table first. Let's look for the ones. By the way, Abe, no, the truth table is not always given, but you can be given a question like this, and then you formulate the truth table, just as we were discussing, and then you use that truth table. I mean, you could be given a truth table, but I never give truth tables. The question will usually be, I stated for you this statement or scenario, you do a truth table in part A, in part B, you can use K-map or use, and then part C, you draw the equivalent simple circuit. So yeah, you are never really, no one will give you the truth table really. But it should be very easy to get it. So let us look for ones. A inverse, B inverse, which is here. And then C inverse D. C inverse D is there. C inverse D, so that is the box. We have a one there. The next one is A inverse B and C inverse D. A inverse B and C inverse D. We have our next one there. Then the next one is AB, which is here. And then C inverse D, which is that. And then finally, everything one. So AB and CD, which is one. Then we know that the rest are all zeros. Alan, I'm going to answer that question when we get there. We have not yet started looping. Otherwise, I would have already told you how we loop. Okay, now, what if I had been given that equation? Actually, when you are given an equation, especially with all the parameter or the variables, then it can be quite easy. So here I see A inverse B and C inverse D. I just put there. A inverse B, which is here, and C inverse D. I just put there, and so on and so forth. So you can see that if you are given this original equation, it is very easy to still fill up your K-map. But sometimes you may not be given an equation like this. You may be given an equation that already has that has already been simplified a bit, meaning some variables are probably not there, and then you are trying to fill the K-map. That's a little bit tougher, but by the time we go through this, you'll be able to understand how to do that as well. Right, so let us look at the looping.
Sir.
Yeah.
Excuse me, sir.
Yes.
I'm wondering about this. From here, this came up for the 4 input. They're saying we have A, B, C bar, D. It's a
Mm.
1. But as if in the table it says 0.
Can you just ask again?
Here in the truth table, the second
Yeah.
last row, we have A, B, C bar, D, which is giving us a 1. No,
This
no,
one
no,
here.
I'm meaning, yeah, that one.
Yeah.
But as when I'm trying to match it with the ones in the table, as if I'm getting a 0. Let me see.
Yes, actually you are right. There is AB, which is a 1, and then C inverse D is also a 1. Okay, so this should be giving us a 1, meaning that AB, C inverse D is a 1, and that should be there. All right, that should be there. You're right. And if this is AB, CD, ABCD is also a 1. Okay, so that is actually ABCD is a 1 and a 1. Then that means, let us look at this one. This is AB, C inverse D. Where is that?
Excuse me, sir.
AB, C, just a moment. 1, 2, 3, 4. Okay, so we know that that is a 1. Then we know that AB and C inverse D is a 1. So the next one is A inverse B and C inverse D. Inverse B, C inverse D, that's a 1. And then A inverse B inverse and C inverse D, that's a 1. So is this the one? So this is AB.
So the last
C
column
inverse D.
is CD inverse.
Not C inverse.
Which last column?
The top of the labeling, the CD is meant to be CD inverse.
Oh, this is supposed, this one here.
Yes, sir, because it cannot be the same as the last one, which is ABCD.
Like on your K-map, sir.
On the map.
K-map.
On the map, eh?
Yeah, like the last one.
Oh, yeah. You're right. This should be C, B inverse. So there you can see there is a mistake in the book. Obviously, for us, we will not make which means that this is in fact what? Yeah, C, D inverse. Okay, so there is that little mistake and it's in the book, really. It's not if should label the last one wrongly. Oh, okay. See that you guys had already given. So I'm just going to reply just to do something small again, because I think Vivian wants once again to know how to fill the zeros and ones in the K-map. We are really going to do this very quickly, just so that everyone is on the same page. I'm going to create a fictitious problem, okay, which is that we want to create a truth table where X is high when any 3 inputs are high. And I should say only when. So we can have DCBA, all right? Then we have X, so 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Okay, so I'm okay. 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1. The reason why I'm putting this is I like to look at these in parts of 4, not to get confused on the output, to stay in line. 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay, so our truth table says x is high when any 3 inputs are high. Any 3 inputs are high. So clearly this is 0 because all are 0, 0, 0, and 0. Because we are looking for only states where 3 inputs are high. That's a 0, that's a 0, that's a 0, and that's a 1. Because 3 inputs are high, that's 0, 0, 0, 1, okay, and then 0, 1, 1, 1. Okay, so that one, that much everyone is under is on point. We are together. So now we can draw our K-map. And then we will have A inverse B inverse, A inverse B, AB and AB inverse. That's C inverse D inverse, C inverse D, CD, CD inverse. Right, so we are looking for the ones because once we put the ones, we know that all the others will be 0. This one here is AB. If you can see the first 2 states on this side, AB, and then C, D inverse. Okay, because here only D is inverse, and I'm writing it in this form just to help me to do it better. But I can also say, I know that C is a 1 and D is a 0. So that is C, D inverse. C, D inverse is in that column, right? That is the column I'm looking at. Then AB, okay, because you can see that B is 1 and A is a 1. So I'm looking at that row. So where they meet is where I put a 1. Somebody is making noise, eh? And that's Jesse. Why is Jesse making noise for us? Then I come to the next one here. Again, here you can see that A, B, okay, both are 1s, so I'm looking in that row. But now for the columns, I'm looking at C inverse D because C is a 0, D is a 1, right? So that's C inverse D, which is that column. So I can put my 1 there. Then I come down here, I see that now A is 1 and B is a 0. So that is A, B inverse, which is that column. I'm looking at this one. And you guys, so we have A, B inverse, and then here we have CD because you can see C and D are both 1s. So A, B inverse, and then CD is that column. So where they meet is where I put a 1. And then I come to the next one, which has a 1. Again, I have CD, all right? And here I have A inverse B. Now this is A inverse and B. A inverse and B is that column, and then CD is that column. So where they meet is where I put my 1. And then finally, I have, this is AB clearly, and then CD, right? Because both of them, all of them are 1. So I'm looking at this, and then that, and then I have another 1 there.
Excuse me.
Since the 1s are finished, the rest are 0. Yes.
I have a question. That what do you depend on to give it an inverse? For example, if I had to answer the same, maybe to fill the same truth table with X is high only when any 3 inputs are low. You depend on to give a certain parameter an inverse.
I mean, if I don't know what you mean by that. If for this next one, that statement you have stated, the truth table would look different. So now if any three, that would be as you said, if any three are low, that would be a 0. That now would become a 1, a 0, and so on and so forth. Now already we have these states do not change, but you just need to look at this, you know, at this one here where we have a 1. And where we have a 1, you look at the states. I mean, A is a 0. So if A is a 0, it is inverse, right? And B is a 1. So B is in the 1 state. Then C is a 0, meaning that C inverse, and D is a 0. That means D inverse. So if a value is a 0 in these truth tables, we take it as an inverse. And if it is a 1, we take it as the normal form. On the K-map, all right, but you said only 3 inputs. Yes, I said only 3 inputs. When only 3 inputs are high, but you can see these scenarios are only when only 3 inputs are high. I was just saying the gentleman who spoke, for him, he said, what if only 3 inputs are low? And I'm saying, yeah, you can see in this state, 3 inputs are low, so I have a 1. Here, 3 inputs are low, I have a 1. If 4 inputs are low, that's not a 1 based on our statement. Yes, yes, thank you. A, B, C, D, if all of them are low, those are 4. Yet we have said only 3. So also, you know, you need to be very careful when you read these statements. If it is only 3, that doesn't mean that it is 3 or more, right? It's just only 3. Okay, so, you know, I know that students find sometimes K-maps a bit challenging, but really they are the very easiest. Once you know how to populate your K-map, and now we know how, then you go to the looping, and the looping is very easy. Yes. Yes, please. Yes, somebody wanted to speak. Okay. For those ones, I see that Mukala's Ivan, you have an issue with the network, so that is your issue, really. But you see, it doesn't matter.
I wanted to say something.
Yeah. Please go ahead.
Yeah, the statement is saying truth table where X is high only when any 3. Then I think, doesn't that make ABCD a 1 also? So you're saying any 3.
By the way, we might have a mistake. X is high when only when any 3 inputs are high. Okay. Okay, so that should be a 0, by the way, right? I don't know if that is what was confusing you, but I think that should be 0 because we have said any 3 are high. It doesn't mean, that's why I added only when any 3 are high. It doesn't mean any 3 or more, right? So I think that is actually a 0, meaning that we would have a 0 there. Okay, I hope you agree with me. Now, if I had said a majority of inputs are high, then of course that would make this one also a 1. All right. Okay, but right now we are not trying to interpret the statement. We are just trying to get any kind of truth table and put it in the K-map and see how that goes. All right. Does brighter SIM, does arrangement matter? A, B, C, D, or D, C, B, A? Actually, it does not matter how we arrange our truth table here. It doesn't matter. But when we are extracting the information to feed it in the K-map, make sure that you are doing the right thing. All right. I mean, this would have been, perhaps it is easier to have A, B, CD, because that one just maps nicely into this, the way these statements are written. But even if it is DCB, it doesn't matter, but just make sure you are picking out exactly the correct information. And then, so why would we use a K-map if we can use a truth table to do the same operation? Vivian, the truth table does and the K-map do not do the same operation. No. Now, we are going to see in a moment when we do loops that we can simplify this, the truth table. You cannot simplify your equation, your statement or whatever your circuit using the truth table. In fact, when we get the truth table, we make a sum of product statement, and then we simplify using either K-map or Boolean algebra. So the statement perhaps you should be asking is, why would we use a K-map when we can use Boolean algebra? That's okay, that is a valid statement. But actually a K-map, in my opinion, is an easier way to process your equation, because very simplest form, if you do it correctly, it will always take you to the simplest form. Whereas Boolean algebra, you have got to go through different stages to get the simplest form. You saw even here in class last time, we were making mistakes and we were looking for theorems that some of you may not even remember, and so on. In fact, K-maps do not substitute. K-maps substitute Boolean algebra, as simple as that. But also, just so that somebody doesn't ignore something, I usually sometimes say or use K-map to simplify. If I don't make that statement, then you can use whichever method you want. So why would we use a K-map if we can use that Vividrin? Is it a must for the output to be? I don't even understand what you have just said. We only need a sum of products if we are going to use Boolean algebra. If we are going to use the K-map, we don't need to formulate a sum of products form. It is not, you can do it, but it is not really necessary, because we have seen that we can go from the map straight, from the truth table straight into the map without first looking at a sum of products. This statement is NA3, not only 3. When only, I think the only is only when 3. Okay, let us remove NA. Only when 3 inputs are high. I think that is perhaps going to make it, because now we have been invaded by people from SMARC and they are teaching us English. It's only NA3. Okay, but however you understand it, that was really not the main gist of what I was trying to explain here, but I guess it's okay to still understand. But I've said now, only when 3 inputs are high. I hope that doesn't mean also 4 inputs high makes, puts it in the high state, whatever. Cool. So let's move on, because we have run out of time. Let us look at some extra examples. So this is what we have now done. Now we have created a truth table and we have transferred that truth table into the K-map. Now we want to see how does the K-map actually simplify our circuit to the simplest form. And we do that using loops. We do loops. So this is looping. Just a bit of, just a moment. So this is just going to be, I'm going to talk a bit about, okay, that has refused. This, for your information, this is the word loop. So when we loop, we combine 2 or 4 or 8 or 16 ones. This is really, if you notice, this is a power of 2. So if 2 ones are next to each other, we can loop them. If they are 3, we cannot loop 3 ones. A lot of you will end up looping 3 ones and I'll laugh. We only loop ones in powers of 2, the number of ones in powers of 2. So either 2 or 4 or 8 or 16. Unfortunately, in our biggest map, which is the 4-input map, the total number of states are anyway 1, are 16, and so we really don't have. But if we had bigger maps, we can loop 32, we can loop 64. Again, we loop the number of ones, which is a power of 2. If they are 3 or 5 or 7 or 6 or 8 or 9, we don't loop that group together. Secondly, the most important, another most important thing is that diagonal loops are not allowed. They are banned. We have square or rectangle loops. Yeah, it's actually here. Either square or rectangular loops. So our loops can look like this, can look like this, can look, you know, like that, where we have maybe 1, 1, 1, 1, or we have 1, 1 here, or we have 1, 1 here. We can have loop 4s, stuff like that. But we should never loop that kind of stuff. I see people sometimes do that kind of stuff, and I know they don't attend class. They don't attend class, so that's why they loop like that. Now this one, we can see that this one is adjacent to that one, but the loop, if we were to loop them together, they would be diagonal, and that is not allowed. So what we do is we can only loop that one together, and we can loop that one together. By the way, always combine as many ones as possible. So if you can make a loop of 4, is better than a loop of 2. I don't know. I'm using this to mean better than, not greater than. Anyway, okay, make sure all ones are in a loop, right? All ones must be in a loop. Secondly, do not loop any zeros. So zeros should never exist in a loop, but ones should be in a loop. Finally, use as few loops as possible. Remember, each loop will give you an expression, right? And so if you have 2 loops, you are going to end up with 2 expressions. If you have 4 loops, you're going to end up with 4 expressions. So that means that the fewer the loops, the better. And anyway, that is really the only way you're going to end up with the simplest form. So if we look at this, we cannot loop these ones to each other. We can, if we were to loop them together, they would create a diagonal loop, and a diagonal loop is not allowed. So we are forced to loop them individually. Now, if we loop this individually, we can see that this loop is called A inverse, B inverse. Okay, so you can see it is between, you know, this is very easy actually. And this loop is going to be AB. And in fact, this we had already seen. We can then say our output is A inverse, B inverse, or AB, which we had already seen at the beginning when we were looking at the K-map. Let us look at this one, which is a little bit more complicated. We want to loop all ones, okay? So how many loops do we have now? We can loop this one and that one because they are adjacent to each other, and the loop would not be diagonal. So we can create that loop. Now we are left with this one and that one, and they are also adjacent to each other vertically or in the vertical plane. So again, we can loop them together because they are adjacent to each other, and the loop would not be diagonal. Now, when we look at these 2 loops, we have actually looped all the ones. There is no other one that is outstanding, and so we can stop there. If we look at this now, let me see the expression retained. This last statement says that the expression retains variables that do not change across the loop. So for example, this loop here, what is its expression? We look at this side. We look in both directions. You can see that you have a 1 in A inverse B inverse, and also this one really corresponds to A inverse B inverse. But across the loop, if we are looking vertically here, we can see that for this loop, for this position, we have C inverse in position C, meaning that C has changed. Rachel Gaju. Rachel Gaju, Vivian Arina Itwe, they are just making noise for us. I don't know why. Okay, so let me just re-explain this one. By the way, these maps have been given to us. So I'm looking at which variable along this loop has changed. You can see that for across the loop, A inverse B inverse hasn't changed because this one corresponds to A inverse B inverse, that one corresponds to A inverse. This one corresponds to C inverse, that one corresponds to C. Because the loop changes across the C dimension, C disappears. That's why you see we say that the expression retains variables that do not change across the loop. Now, across the loop, A inverse B inverse hasn't changed, but C has changed from C inverse to C. So C will disappear. You can see vertically that both ones belong to C inverse. So C inverse will already be there. But across now on this side, right? On this side, you can see that this one belongs to A inverse B, whereas this one belongs to AB, meaning that A has changed from A has remained the same. So the one which hasn't changed is what we retain as B. And then it means that now we can write our X as A or B C inverse. And believe me, that is the simplest form possible. All right. Let me also say something that if we make a loop of one, we do not eliminate any. We do not eliminate any variable. A loop of 2, we eliminate one variable. A loop of 4, we eliminate 2 variables. A loop of 8, we eliminate 3 variables. But you can see it is really 2 to power 3, 2 to power 2, and so on and so forth. You are going to get this as we go along. So let me, okay, let's see. I beg your pardon on the looping. Yes, I'm sure, excuse me, sir, pardon on the looping. Okay, so let me just do it again. We are here to study, so I don't know why this thing is not working. It's actually refusing to work, and okay. So let me just do the looping again for you. Loop adjacent ones in rectangular or square, right? Or square boxes or loops. Number 1. Number 2, loop all ones. Make sure that all ones loop. Do not loop zeros. 4, avoid diagonal. In fact, it is not avoid, they are banned, they are not allowed. Avoid diagonal loops. 5, make as big possible, and so on and so forth. So 5 and 6, across each loop, for us to extract the equation, across each loop, retain variables that do not change. And I think this is the statement that probably is confusing you guys, this last one. So we will start with, you can start anywhere looping. Now we clearly see that these two are adjacent to each other in a rectangular form, and we cannot make a bigger loop, because if we had said, for instance, let me just use this to illustrate. Assume, for instance, that we had a 1, a 1, a 1, and a 1. Now, this is a 0. So if we made a bigger loop of 4, it would encompass that 0. But if this was also a 1, then we would be better off looping all those 4, because they are adjacent to each other and they form a square. But the reason why we don't do that here is because that's actually a 0. Now, once we have looped these 2, we are left with another 2, and luckily they also form a square loop. And then we are done there. But if we had done this, okay, so I'm going to get back to this. Let's first do this one, which we've got from the book. Now, this loop, how do we get its expression? Its expression, you can see that vertically, C changes from C inverse to C. That means that variable must go, since it has changed. Across each loop, retain variables that do not change. Clearly, this loop has changed, includes C inverse and C, so that one must go. However, on this side, we can see that both ones correspond to A inverse, B inverse. So that loop actually is expressed as A inverse, B inverse. The C variable has gone. And here we have already said that if we loop 2 here, we are going to eliminate one variable, and clearly C has gone. Now for this one, you can see that both ones in this loop correspond to C inverse. So we are going to have C inverse there because it hasn't changed across that loop. However, if you look from this direction, B is the same for the whole loop, but A has changed from A inverse to A. So that means it is A that goes because it has changed, and we end up with B. Okay, so then of course, your final equation is an SOP, which is BC inverse or A inverse B inverse. Now let us come back to this one. There is another important statement that we need, and that's A inverse B inverse. That is AB inverse, and that is C inverse, and that is a C. So let's say we and that is a 0. Okay. So simply meaning we write expression for only the variables that haven't changed, thereby eliminating the variable that changed. Yes, Kasiswa. And actually so every time you do a loop, you have got to write its expression. And then after you find the expressions from the loops, really the expressions will be equivalent to the number of loops, and then you write your final statement. And now you can draw your equivalent circuit if it has been asked for. Daphne, yes. How about looping the 3 vertically? Amanyire Stevens, I already said you cannot loop 3 ones. You loop either 1 or 2 or 4 or 8. You know, Mugerwa has answered you. Good stuff. Now, let us look at this one. Now, this one, we are lucky that this one also has a 1. And I said that we should loop as many ones as possible. That reduces the number of loops that we have to do. In fact, That is the only approach that gives us the simplest form. So here we see that we have ones that are adjacent to each other and form a square, right? So that is a big loop, and we expect to eliminate 2 variables, isn't it? Because we have a loop of 4. Somebody is making noise. Joel, please keep muted. And so let us even actually now try and to extract this one. Now you can see here, this loop C changes from C inverse to C. In other words, the ones here, some are C inverse, some are from C. So C will be eliminated. Also, when we look from this direction, we can see that A inverse is constant, but B changes from B inverse to B, meaning that B will also be eliminated, and we end up with A. In fact, A inverse, sorry. In fact, that loop has simplified our equation to A inverse. Whereas here, because we were making loops of 2, we ended up with 2 variables, but because here we made loops of 4, okay, so we have seen that. Okay, we can see that a bigger loop has ended up giving us a simpler expression, in this case, A inverse. Right. Oketa, there is nothing like we have an A that can't be looped, or a one that can't be looped. Even if it's one and it's isolated, we just loop it. So for instance, here, we have a 1 here. Now, this is the other thing I want to say, and this is very important. You can re-loop looped ones in order to get the simplest expression, right? But each loop must have at least one that is not yet looped. So there is, there are too many rules, but actually in the working, it's quite easy. So only we have this one, it is not yet looped. We must loop it. We cannot loop it with these zeros, but we shouldn't loop it alone. This statement is saying that actually, much as this one is already looped, we can still create a loop that uses that one, all right? But we should make sure that at least one, of course we had this one which wasn't looped, but we can loop it with as many adjacent ones as possible to end up with a simpler expression. But at least we should make sure that we don't create a loop of all ones that are already looped. At least one of them should be unlooped. Now, we can actually loop 1 with 7 already looped ones. That would be okay. But so in other words, when you have a scenario like this, you should make sure that you don't group this one alone. These loops do not have to be mutually exclusive. You can now create a loop that actually uses that one much as it's already looped, because that creates a bigger loop. And if we do that, we are going to end up with C inverse is not changing clearly across this loop because it is vertical. Okay. The only change is happening on the horizontal side, or is it the vertical? I don't know, it's a horizontal side, where we are looking at A inverse B in this position changing to AB, meaning A has changed from A inverse to A, which eliminates it, and we end up with BC. So now our expression here becomes A inverse or BC inverse. Do you see the difference that one has made? Is that instead of having this, we now have a simpler equation just because we added a 1 somewhere. Right. Excuse me, Sir Pardon, on how you have got the A inverse. Okay. The A inverse. The A inverse has come from the bigger loop. I don't know where to draw it. Right. So we see here that if we loop this, remember this is C inverse and that's C, and that is A inverse B inverse, and that is A inverse B. So here for this loop, C, we can see that C is changing from C inverse to C across that loop, from here to here. On this side, we have this box and that line, this row and that row. In this row, we can see that B changes from B inverse to C, but A remains constant. So that means our expression
A inverse
resolves into A, right? So that is how we ended up with A inverse. If I loop AB alone, is my answer correct? No. Techno, I don't even know what your name is. But no, I've already said that if you only loop AB, you are not going to end up with the simplest answer. Let's try. Let us try. I told you people to use your names. You don't learn. That's a 1, a 1, a 1, a 1, a 1, a 0, and a 0, and that loop. And then you have that loop. Now, if you have this loop, we already know this is A inverse. If you have that loop alone, AB, C inverse. Okay, so now your X would now become A inverse or AB C inverse. Whereas if we had looped it with is equal to A inverse or B C inverse. Now you remember the theorem which says that XY is equal to X inverse or Y, right? Meaning that this statement can be reduced to A inverse or BC or BC inverse, which is actually that. The fact that this final statement can be simplified further means that your K-mapping or your looping is wrong. That's what I was saying at the beginning. If you do your looping wrong, meaning you don't create as big loops as possible, then you are going to end up with an expression that can be simplified further. And for me, I'll just not mark you correctly. I'll just give you a 0. Usually I mark per loop. So if a loop is correct, I give it a 1. If it's not, I give it a 0. So here you would get 1 out of 2 marks. All right, can I still come up with my, please don't send me directly. You send to the rest of the class. Can I still come up with my outputs without the truth table and proceed to come up? How will you come up? I don't know, but anyway, don't worry about that. I'll probably ask you to do the truth table anyway. So it's not like you can avoid it. But also I think you need the truth table to fill the map correctly. Otherwise, it would be very difficult for you to do it correctly. So I would recommend the truth table in all cases, even if I've not asked for it. In fact, sometimes I don't ask for it because it's obvious. How are you going to do this without creating a truth table first? Okay. Yeah, still have 30 minutes.
I'm aspiring for most projects coordinator. I opened it is the day I'm doing there.
Yeah.
So today's an lecture, so I don't want to take a lot of your time, but I'm here so that you see me and tomorrow comes, you can change your mind. Vote for me.
Excuse me, sir, you are muted.
Excuse me, sir. I can't hear you.
Okay, so welcome back from the break. So we had taken a 5-minute break. It's over. Let us continue with the lecture. So we are going to look at now something like this. Something like this is very easy. You can see that you have this loop and that loop. Okay, there is no other loop, and you couldn't combine more than more than 4 ones here because they wouldn't give you the shape that you are looking for. So you combine the two. And we have already seen how we extract information. So if we look at this loop, each of these loops will eliminate one variable because they are two variable. They are two state loops. In other words, each loop is combining two boxes. So if we look at this loop, we want to know, you can see that each loop, both ones correspond to C inverse D. So already C inverse D will be there. We are not eliminating anything since it is not changing in that direction. But in this direction, we can see that this loop includes A inverse, B inverse, and A inverse B, meaning A inverse is constant. It is B which has changed. So that loop will be A inverse CD. This loop we see corresponds completely to AB. So already AB will be there. But across this direction in the vertical plane, we can see that here we have C inverse D, whereas here we have CD. In other words, C has changed from C inverse to C, whereas D is constant, D, D, meaning we have A, B, D. And we can see that because they are both two state loops, they only eliminate one variable. In this case, we've eliminated B. In this case, we've eliminated C. And our statement becomes X is equal to A inverse C inverse D or A, B, D. And this is the simplest statement. You cannot have a simpler statement. Let us try to just see what would happen if things were different. If things were different and we had a 1 and a 1 and a 1 and a 1 and a 1, how would we do this one? Instead of now we can see that you should always look for the biggest combinations first, all right? So here we can see we have these 4. And we know these 4 will eliminate two variables, okay? So that is already, you know, and then we have this one which is left alone, but we know we can loop it with that one. Okay, so we can make another 2 variable loop, but let's assume that we had another one here, meaning that there are 6. Obviously, we could not loop all the 6 together because that would not be allowed. We can loop 2 or 4 or 8 or 16. So our first loop is still okay, but when we loop these ones, we can loop them like that. In other words, we can make another loop of 4. We shouldn't make a loop of 2 because actually they have another 2 that are adjacent to them, only that those are already, you know, only that those ones were already looped, the 2s, but we know that we can still loop them again. The rules allow us. Okay. Let us now look at, so you can see this is the stuff that we have been doing. Yes, any question? There is somebody who is unmuting themselves and I don't like it. So we would have Tracy.
I wanted to ask for an input to be eliminated, does it have to be from the inverse to the normal input, like from C inverse to C, or it can be from C to C inverse?
Yeah, either is fine. It can be from C inverse to C or C to C inverse, as long as it changes. The important thing is that the variable has changed.
All right.
Okay, so let us say, now the thing I was talking about, which was 1, if we had the 1 and the 1 and the 1 here, actually these ones are adjacent to each other. In fact, let me do, is what I'm doing correct? I don't know, but we are going to be seeing a number of these. Joan?
Was by mistake, sorry.
Joanne? Okay, so these ones, these four corners are adjacent to each other. So if you see something like this, then you can make a loop. You know, we have one loop. This is actually the center of the box, but it is actually one loop. We draw it like this one. If I have something like this, okay, try and give. If I have 1 and 1, but this one on this side is a loop of 4 ones. Here, if I have a 1 and a 1 here, but no 1 here, then I cannot draw this loop and that loop. Okay, so that loop is 2. I cannot loop this one with that one because it would be diagonal. You can see. But I can now make a second loop. So this is loop A. Let me call it loop A. Now this one is not isolated because it's actually adjacent to this in a vertical, in a horizontal way. So I can actually loop this one and that one again, and this would be loop B. Okay, these are a bit confusing, the ones in the corners, but with experience and with more practice, you will get them. So let's first forget about this. Let us try to resolve this one. What would the expression be? We know that this is the same loop, A, and A, because they are adjacent to each other. We know that because we have 4 ones looped together, we are going to eliminate 2 variables, right? Out of these 4. So let us first start with the upper side. We see this one, these 2 ones, luckily they are in the same vertical plane. We see that the variable changes from C inverse D inverse to C D inverse, meaning that actually C has changed from C inverse to C, D has stayed. So we have a D. If we look on this side, the ones are corresponding to A inverse B inverse and A B inverse. So again, changing from A inverse to A, whereas B inverse stays constant. So our output becomes actually the loop for this A. Let me call it A. The loop actually resolves to B inverse D. Right. Let us move on. Is it D inverse? Yes, it is D inverse. Thank you. It is D inverse. Now this one we know. Okay, so this clearly is going to be, what will this one be? How do we resolve this? I am waiting. Okay, so B, C inverse, yes. B, C inverse. What about this one? This other one, it is A inverse B. Yes. Thank you. I've seen you've got it. How do you account for the number of variables to eliminate? Musa, it is very easy. If you loop 4, you eliminate 2. If you loop 2, you eliminate 1. If you loop 1 alone, you don't eliminate anything. If you loop 8, you eliminate 3 variables, which is 2 to the power 3, right? And so on. So it is 2 to the power 2, 2 to the power 3, and so on and so forth. If you loop 16, you eliminate everything. As simple as that. Thank you. Yeah, so you can see the K-map helps us to move from here to there. You don't need to first do this. Here, the K-map helps us to move from here to here. You don't need to do that one. By the way, this is a step in the book that they add for you to just see. It's like saying this one corresponds to A inverse B, C inverse, and that one corresponds to A inverse B, C. And you can see that when you get the common factors, you'll end up with C or C, which gives you A inverse B. So what the K-map is doing is imitating the Boolean algebra, but actually taking you straight to the final simplest equation. This is something that we have seen. This one is adjacent to that one, again, because it wraps around like that. So you should always remember that. And if you don't, then you will look at these as isolated ones and loop them individually, and you'll end up with an equation that is not as small, that is not in its simplest form. Okay, so so this is x is equal to C inverse, clearly, because they are all corresponding to C inverse, but on this side, from this point to that point, B hasn't changed, so B inverse of C. If you look at this one again, you can see that you have a one here and a one here, and they are adjacent to each other. And then also that loop. This loop is actually now going to be A inverse, B inverse, because you can see it corresponds to both of these. And then on this side, C is the one which does not change, D changes. This one is AB inverse. And then here, you can see that on this direction, we change from C inverse to C, but D inverse is the same. So we end up with D inverse. Let me give you something. But before I do that, let's just continue. Doctor, isn't it B inverse, C inverse? It could be. Yeah, B inverse, C inverse, yes, because this is C inverse. Yes. Here, okay, so this is what we are getting, which is this and that. Ignore this first statement. You're going straight to the last one. So let me give you an something that I want to see if you've understood. Please, if you fail this one, it doesn't mean that that you are not serious. It is just an example. With this one, you would have to do so many loops to actually get the approaches in your mind. So you are not, there is no pressure for you to pick up everything today. Okay, so I have a one, 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 a one. What is my X? Let me give another one here. These are all just examples. I have a one, 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 and a one, a one, a one, a one. The rest are zeros, so. Okay. Kasasira Enoch says A, CMP John says A. So if you get A, then don't type it since, you know. But what do the others think? Anyone has a different answer? The guys who have finished this one can start working on this one. Okay, so the guys who have got A, I think have got it. Probably, I don't know. Douglas Chivumbi has got C, Magambo Morris has got D. I like the guys of C, and if you have got D inverse, it's okay. It's okay now, I've seen it. If somebody has already typed your answer, it's okay, not, you don't have to type it. Okay, so the loop here is going, because this edge and that edge are actually adjacent to each other. This edge is also adjacent to that edge. So if this edge is adjacent to that edge, it means that these ones are adjacent to those ones. And so we can create a loop like this and another loop. You know, it is the same loop. It is not another loop. It is the same loop, a loop A, meaning that these we have a loop of 8 ones. Okay, and you can see that across here and here, what changes actually is C. C inverse here, C. D inverse stays the same. Whereas across here, actually everything changes, right? Because A inverse changes to A and A, B inverse, B and B. So we have a loop that eliminates completely all of these variables because they are changing across the whole loop, and we end up with our X as D inverse. Number 2, for number 2, I see most people are saying that the answer is D inverse or C, okay? If you have D inverse or C, you don't have to type it. But basically what they are doing is, we want to create the biggest loop, so we can start with this one, right? And then we will be left with these ones, but these ones are also adjacent with these ones. So we can create another loop that already encompasses those ones, but also includes these ones that were already looped, but they are adjacent, so we can loop them. Now, interestingly, we already know this is D inverse because it is similar to that. But what is this loop here? In this loop, if we look across here, if we look from these directions, all of these are eliminated. All these will be eliminated. But across here, we see that what is constant, that our X is equal to C or D inverse. And you can see that when you create huge loops, if you are lucky to resolve those huge loops, statements indeed. Douglas Chivumbi, I don't know where you got that, but even if that were true, I think it can be, you would have C. No, you don't have that. Tumusime Abraham, you can ask.
Yes, excuse me, sir. What if you use like another loop and after getting like an expression you simplify? Is that okay?
That is wrong. I will not give you a single mark for that because it means you have failed. Abemasko, you are in town. It means you have failed the looping. Okay. If you cannot loop well, then you don't deserve marks. I know you are worried that what if I don't know how to loop and I still get the final answer. The final answer will not mean anything to me if your working is wrong. Okay, so we have here we can see that we are looping 4. So we eliminate 2 variables and we know that all these will go because the loop is crossing all of them. So our X here is C. Here, this loop is crossing Kadodo Vanessa.
Yes, sir. About the previous slide, I'm a little bit confused on the first example.
This
the
example.
Loops and all that. Yeah, that one.
Actually, this example, why I brought it is because probably just to give you, remember I said, maybe you missed it. I said that this thing wraps around and becomes like a sphere. That means that this line is adjacent to that line. So it means that this point here, this line is adjacent to that line, because you can wrap it around like a sheet to make some kind of cylindrical object. So you have, if you have a 1 and a 1 and a 1 and a 1 here, a 1, a 1, a 1, a 1, these are actually adjacent to each other. You have to visualize it in your 3D mind, that this is actually, these are adjacent to each other. That means that we shouldn't loop these 4 individually and those 4 individually, because we would have created a smaller loop, yet we could create one large loop. We would have created 2 small loops, yet we could actually create one large loop. That's why we said that actually our loop is, these ones are together adjacent to these ones, meaning we create the same loop A. And since this is C inverse, D inverse, CD inverse, CD inverse, and because these loops cut across all these variables, all these will be eliminated because they change across. However, if we are looking at this point and that point, where these are the 2 vertical columns where our loop is, we see that C changes, but D does not change. It remains D inverse, which is where we ended up saying that X is equal to D. So why I brought this one was just to show you that just because ones are not next to each other on your paper is not enough to say that they are isolated from each other, because we need to remember that this is adjacent to that. That's why earlier we were drawing loops like this. You remember this loop, to say that this one and that one actually form the same loop. It's because this line is adjacent to that. If we actually had another one here, then we could make one loop of 4. And I think we did it earlier. We saw a loop of 4 where the ones were in those corners. However, I said that if you have this, let's say you have 4. I said that if you have a 1 here and a 1 here, yes, they are adjacent to each other, but if you loop them, this would be a diagonal loop, which is not allowed. But if you add a 1 here and a 1 here, then you can actually now create a square. It would look like that in reality. So yeah, so this is, and then the other example was that what if we add another 1, 1, 1, 1? Then we can loop these ones, but because they have other adjacent ones that allow us to make a larger loop, then we can actually now encompass those ones to create one other loop. What if we had this one? So please go and practice K-maps. Somebody is making noise for us, please. Somebody is making noise for us. So if we had 1, 1, 1, 1, 1, by the way, where I don't write, I just assume it's a 0. And then I have a 1 and a 1 and a 1. The rest are 0. So now we can still have our loop. That's a 1. Our loop, and we know that this is actually one loop A, and A would give us, I think we say D inverse. Now we are left with these 3. We no longer have 4. Here we had 4, but now we have 3. Meaning we can now create this loop. It's quite interesting now what we are about to do, so look carefully. We have this 1, 1, and a 1. So this one can create a loop of 4. You see? So we have a 1 which we are not yet resolved or looped. We can loop them with these 2 which are looped already. And this loop B will give us, on the upper side, on the vertical side, we are going to have C, which is not changing. And on this side, we are going to have B, all right? So we have BC. Now we are left with the 1 which is not yet looped, because remember this one is looped in that loop. This one is not looped. So we can actually, in a loop of 4 with those, meaning that now my loop C actually now gives me once again C, but on this side, I think that's B inverse. B is changing from B to B inverse, so I have A, right? So we have a scenario where we have a one like this one, which has been looped 3 times, which is fine as long as every time you loop it, you are looping some that have not yet been looped. Okay. Hisham, a sphere, a cylinder. It depends. If you're looking at these vertical lines, you can call it a cylinder. But if you're looking at adjacent ones in the 4 corners, it becomes a sphere. So you could say it's a sphere. In which situations do we loop twice? Mugerwa Alex, you cannot loop 6 ones. Do you follow an order, or you can begin with any? Chomjisha, you can begin with any. But Chomjisha, you should try, first of all, before you start looping, you should be looking first for the biggest loop you can make. I guess that should be your starting point. Are there any ones that are as many and adjacent to each other that I can loop? And then from there you go. If you get the biggest loop, then you can start now looping the ones that are left alone, are not yet looped. But in general terms, you can start with wherever you want. There is no general rule. But perhaps what I can say is that try and make as big a loop as possible, first of all. Cool. Okay. So I hope that answers your question, and I think it was Kadodo. Here we see that AB, this loop changes across, it just changes all of these, meaning all of those are eliminated, and we end up with actually AB, because these ones are all corresponding to AB. Here, this actually we've already done. Across this dimension, C changes, so we end up with D, and across this dimension, B remains constant, A changes, we end up with B. So our X becomes B. Another instance that we had not yet seen. Again, this line is adjacent to that line. So if you have ones on this side and ones on that side, please be careful, because they might be adjacent to each other. So this loop is the same as that loop. It is both loops. Look across here. No, not across. If we look in this point and that direction where our ones are, we can see that C changes and we end up with D inverse. And if we look across here where our ones are, again, B changes. So we end up with A, D inverse. This is the one we have already seen. We already saw that these are ones that are looped together because they are adjacent together. If you pull those 4 corners, they should touch, and then you have four ones adjacent to each other in a square, and that will give you, if you look at this, it will give you D inverse, and if you look across here, here and there, you will have B inverse. Kasasra Enoch, I don't know where you got A or D or D. And then, let me see. We have already gone beyond our time. Okay, so I think we can, let's just look at this one, and then we can call it a day. We can always continue next time. But you can see for this one, it changes across this whole dimension. And on this direction, B remains. So here X is equal to B. And we know that's the reason why that is because we have looped 8 ones. When you loop 8, which are octets, you eliminate 3 variables. Here, what remains here is C inverse. All these go. So you have X is equal to C inverse. Now, if we were doing our Boolean algebra, we would have had to get our sum of products, which would be this one, which is A inverse, B, C inverse, D inverse. We add that one, which is A inverse B, C inverse D. We add this, which is A inverse B, C, D, and so on until we end up adding that one, C inverse, C, D inverse. And then we simplify this one, and then we would end up there. You can try it. But the trick is that you must loop correctly. Okay. All right, let's stop there. Do have week. I believe that you are doing the assignment, the group work. Please, if you did not do if you didn't form a group, don't do group work because I'm not going to. After this group work, I'm going to allow people to form new groups, so you can.
Excuse me, sir.
Yeah.
Excuse me, sir. Yeah, we are doing the group work, but personally, we found a challenge in generating the timing diagrams because the tutorials you gave us are not explaining clearly. When you practice what they're explaining, you don't get the timing diagrams correct. Yeah, that's the challenge so far we have.
I don't know, because I've done the assignment, I don't really give any work without doing it first. And I've got the timing diagrams correct. So I don't know what could be wrong. But by the way, if you are in a group of 4 or 3 or whatever, each one of you can do the work on their own so that, and then you come together and do together the final work. Basically what I mean is that you might find that either you as a group, you are having a problem and you are doing it all together. You might find another group is not having a similar challenge. So maybe you can consult them or just keep working on it because I think it's possible. I've done it myself and you still have time, so it will work out. Okay. Right. If all outputs are 1s, do we get 0? Hisham, that's good thinking. You should think about it. If everything is 1, everything, then you are eliminated. I mean, let me just actually, it's quite interesting. So if everything was a 1, what is my x? My x is not a 0, it's actually 1. But that really comes from the truth table, DCBA. If all your options 0, 0, 0, 0 to 1, 1, 1, 1 are 1s, then it means everything is 1, right? That's not even a circuit, because what is that circuit trying to do? Since every combination gives a 1. Yeah, Douglas, those who have no groups did not form groups. Let me tell you something. I am just trying to teach you to be responsible for yourselves. If I tell you that please form groups and I give you 2 or 3 weeks and then you still refuse to make them, it is really no longer my problem and I have no sympathy. And you guys, I want to tell you that you should have no sympathy for anybody who is not serious in this university. Eventually they will wake up and you hope that it is not too late for them. Have a nice week.